Nikola Tesla once solved a problem engineers thought was impossible by removing the moving parts entirely. A few commonly used one-way valves are shown here. All these valves have one thing in common. They all have moving parts. Here is a design challenge. Is it possible to design a one-way valve without any moving parts? Most of us will feel like this is an impossible design challenge. But not for design genius Nikola Tesla. Nikola Tesla developed a one-way valve without any moving parts. In his patent, he named this valve a valvular conduit. In this video, we won't only learn the workings of this valve. We will make an attempt to understand how Tesla's mind worked during the development of this brilliant product. Let's consider this design. A simple channel with some undulations on the walls is shown. These types of undulations provide the same amount of resistance to flow when fluid enters from either side. Now take the second case. Here, the obstacles are added at an angle. Here's a question for you. In which direction will the fluid find it easier to flow? Left to right or right to left? Your intuition says that the right to left flow is easier, doesn't it? Why is this so? The flow is of the converging type when it goes from right to left, but the diverging effect will take place when the direction of the flow is reversed. The physics of converging and diverging flow are quite different. In converging flows, as the area reduces, the velocity will increase along the flow. This velocity increase means that the pressure will drop along the flow. For diverging flow, the case will be exactly the opposite. The pressure will increase along the flow. This pressure increase is called an adverse pressure gradient condition. As the pressure increases along the flow, the fluid particle decelerates along the length. And after a particular length, flow reversal could occur. This reversal will lead to flow vortices and energy losses. In short, diverging flow is a difficult flow to maintain. It offers far more resistance than a converging flow. Let's rearrange the obstacles. Here, a few obstacles are connected to the wall, and the remaining ones are made smaller. Let's examine what happens to the flow when it moves from left to right. You guessed it. Here the flow is getting divided into two parts along with the flow divergence. After this, the secondary streams are directed to mix with the primary stream at almost a 180-degree angle. This process is similar to mixing two jets from opposite directions, which results in whirling of the flow and losses. This design will obviously produce more restriction than the previous design, and this process will repeat at every pair of obstacles. When the flow goes from right to left, it passes very easily without much obstruction. Let's make a few more geometrical modifications to this design. The previous design is a mirror reflection. Let's shift the lower portion as shown. Now the width of the obstruction is increased. What you've got now is Nikola Tesla's design, the Tesla valve. In the Tesla valve, the flow is always divided into two streams. The straight line flow is the primary stream, and the diverted flow is the secondary stream. In his design, Nikola Tesla cleverly integrated all the interesting fluid mechanics we have learned so far in an optimum way. Now let's see the detailed fluid mechanics of the Tesla valve. Let's consider the right to left flow first. Initially, the flow is divided into two streams. Obviously, the secondary flow will be very low since the fluid has to take an unnecessary turn to enter that region. This means the majority of the flow will be through the primary stream, and it will go almost in a straight line without much obstruction. When fluid enters from the left, the flow again gets divided into two streams. In the bottom section, the flow diverges, and the adverse pressure gradient will make life difficult for it. The second stream hits the bucket-like structure and loses its momentum. After this momentum loss, the flow takes an approximate 180-degree turn, which again causes flow losses. After all these hurdles, this stream mixes with the first stream from an opposite direction, resulting in further energy loss. In short, when the flow goes from left to right, it undergoes a huge amount of obstruction. This process of sudden expansion, deflection, reversal, and mixing will take place at every unit. By adding many such units, the resistance can be further increased. Let's test the Tesla valve by connecting it at the outlet of a running pump. If the valve is connected in this direction, you'll notice a good amount of flow through it. Obviously, the pressure drop across the valve will be negligible. Now connect the valve in the reverse direction, and the flow becomes drastically low. The pressure drop across the valve will be huge. The Tesla valve cannot block the flow completely, but this single-piece valve is highly durable, since it provides more resistance to the flow in one direction without any moving parts. It has found research applications in microfluidics and pulse jet engines. It is used along with a micro pump to deliver fluid in very small quantities, as small as 3 milliliters per minute. Model valveless pulse jet engines use the Tesla valve to replace the Reed valve in conventional pulse jet engines. We hope you are able to understand how Nikola Tesla's mind worked in developing this product. Please be a Learn Engineering member by clicking the support button. Tune in soon for another video.